explains for the particular solution y of x of the differential equation y squared x dy over dx minus x plus 1 equals 0, which satisfies the initial condition of y1 equals 3. For part B, under certain ideal laboratory conditions, the surface temperature y of the object changes of time at a rate proportional to the difference between the temperature of the object and that of the surrounding medium, which we will assume is constantly y naught, which also equals dy over dt equals k multiplied y minus y naught, where k is a constant proportionality of and is less than 0. What is the most general solution of y and y and t to the above differential equation? Suppose a corpse, this is for part C. Suppose a corpse is found at noon and at a moment has a temperature of 87 degrees Fahrenheit. 1/2 an hour later, the corpse has a temperature of 83 degrees Fahrenheit. Assuming that the normal body temperature is 98.6 degrees Fahrenheit, and that the air temperature is constantly 75 degrees Fahrenheit, determine at what time death occurred. So basically, each of these we are using each formula. Next slide. And for the differential equations, here's our strategy. Inseparable is a differential equation in which the various variables cannot be separated. And it requires a different method of solving than the easier separable differential equations. For separable, the method, differential equation in which the various variables can be properly separated. Easily solved by separating variables onto different sides and integrating. So that's what we're going to do for problems A, B, and C. And for part A, next slide, we're supposed to find a particular solution, as said before, for this equation y squared y of dy over dx minus x plus 1 equals 0 will satisfy the initial condition of y1 equals 3. And all three should be finishing up part A. Okay, so the strategy for part A is separate y's from the x's and integrate both sides and find the initial value for C.
Okay, so to solve this problem for part A, your first step is going to be to separate the x's and y's. So to do this, you're going to want to get y's on one side of the equation and x's on the other. So your first step would be to add the x and subtract the 1 to the other side. But notice that you still have the x and the dx with the y's. So to do that, you have to do like the opposite mathematics. So multiply the x, or divide the x and multiply it by dx to get your equation of y squared dy equals x minus 1 over x dx. So now you have to take the integral of this. So to do it, it could be easier to focus on one side at a time. So focusing on the y, when you take an integral of a variable to an exponent, you add 1 to that exponent and divide by that number. So you're going to make it y cubed divided by 3. And then for the x side, it will be easier to split up the fraction to x over x minus 1 over x. And that's going to noticing x over x is just 1, you're going to have 1 minus 1 over x. So the integral of that will become x for the 1, and then 1 over x, the antiderivative of that is ln of x. So you have y cubed over 3 equals x minus ln of x plus c. And there's only one c because it counts for both the c's from the y side and the x side. So finally, you're going to solve for c. So to do this, you would plug in your initial value that was given. So your x is going to be 1 while your y is 3. So you plug that into your equation from part B to get 3 cubed over 3 equals 1 minus ln of 1 plus c. Noticing that 3 cubed is 27, you divide that by 3 to get 9. And your ln of 1 just becomes 0. So you have 9 equals 1 plus c. And then subtracting the 1 over to the 9 to get what c equals, you get that c is 8. So now you have to use that and solve part B. So part B, just a reminder, is under certain ideal laboratory conditions, the surface temperature y of an object changes in time at a rate proportional to the difference between the temperature of the object and that of the surrounding medium, which we will assume is constantly y naught equals dy dt, which equals k y minus y naught, where k is a constant. What is the most general solution, y equals yt, to the above differential equation? So to solve part B, you're going to have a kind of strategy to follow. So it's similar to part A, where you have to separate the y's from the t's. And you don't have to worry about k because that's just a constant. And then you're going to integrate both sides of the equation and simplify that to get a simplified equation to solve.
Alright, so the first thing we have to do is separate the y's from the t's. So on the left-hand side, we want dy by itself, and to get dy by itself, we have to multiply by dt over 1, which will cancel out the two dt's, leaving dy by itself. And what we do to one side, we have to do to the other. So we have to multiply the right-hand side by dt, which is why dt appears on the right-hand side. And now we need all the y's on the left-hand side, and we can do that by dividing both sides by y minus y naught. And that's how we get the equation at the bottom. Now the next step is to integrate both sides, and looking at the left integral, we notice that it's 1 over something to the first power. And we know that when you integrate 1 over something to the first power, it's the natural log of whatever's on the bottom. So in our case, it's the natural log of y minus y naught. And looking at the integral on the right-hand side, the case is a constant, so we can ignore it for now. So it's basically just the integral of 1 to respect to t, which is just t, and that's how we get kt. And then it's an indefinite integral, so they add plus c at the end of our equation. Then we have to get y on one side and everything else to the other. So the first thing we have to do is get rid of natural log, and you get rid of a natural log by using e. And what you do on one side, you have to do to the other, so that's why e appears on both sides of the equation. The e and the natural log will cancel out, leaving behind y minus y naught. And another way e kt plus c can be rewritten is e to the c times e to the kt. And then to get y by itself, you have to add y naught to both sides, and that's how we get that equation there. And that's basically it for problem C. That's basically it for problem B, but this is problem C. It basically says a corpse is found at 87 degrees. Half hour later, it is 83 degrees. Assuming that the normal body temperature is 98.6 degrees and that the air temperature is 75 degrees, determine what time of death it occurred. So the equation that we used to solve this one is the one that we found in part B, which is y equals y naught plus e to the c times e to the kt, where y equals temperature and y naught is initial temperature and little t is time. The strategy for finding the answer to this problem is making a list of what you know and what you don't know, and then solving for c, and then solving for k, and solving for t, and then you can use t to find the exact time the death occurred.
Okay, so to start solving part C formally, we will create a list of values, which we will then plug into the 3-step system to solve for C, K, and T, as she said before. These are T equals 0, which occurs at 12 p.m., Y equals 87, which is the temperature when the body is found, T equals 30 when the body is 83 degrees Fahrenheit, Y naught, which is 75, that's the normal air temperature, and Y equals 98.6, which is the normal human body temperature. Solving for C, we will use values y equals 87, y naught equals 75, and t equals 0. When you plug that all in, e to the kt will become e to the 0, which we know is equivalent to 1, so that will drop out, leaving us with 87 plus 75 plus, or 87 equals 75 plus e to the c. And you subtract that over, you get 12 equals e to the c, which when you solve formally will be ln 12 equals c. So for, now that we've solved for c, we're going to solve for k. And we will use the values y equals 83, y naught equals 75, and t equals 1/2, as well as our value e to the c equals 12. When we solve it all out, we get k equals 2 to the ln of the absolute value of 2/3. And now we can solve for t. And to solve for t, we will use y equals 98.6, which is the normal body temperature for humans, y naught equals 75, which is the normal air temperature, e to the c equals 12, and our k value 2 ln 2/3. And plugging them in and solving it all out, just basic algebra, we get t. T is ln 23.6 over 12 divided by 2 ln 2/3. This is roughly 0.83 hours, or about 50 minutes. Therefore, the death occurred roughly 50 minutes before noon at about 11:10 a.m. So our problem required us to utilize separable differential equations. Using them, we will be able to find an equation using multiple variables to find the time of death for a corpse found at noon, which we found to be 11:10 a.m. Any questions?
Why did you do a dead body question?
That's
Ask
what we
Rich.
get.
Wait, didn't you guys have an A through D Yeah, it was just hefty, so I thought it was.
What's your name with the hat?
Michaela.
Sorry I pointed.
It's okay.
Did I do that?
Wait, yeah, can we go back to your name slide?
What's your name? Oh, yeah.
Just
What's your
for,
name? Kay?
Caitlin.
I think I know how to spell your name. T-A? Okay.
Any
Um,
questions about like the math?
E-
AKA.
E-A.
it all makes
AKA.
sense.
Oh, I was right.
Nothing?
Okay.
Not right now. Well, yeah, no.
No?